Our study of magnetically induced electromotive force begins with a look at several pioneering experiments carried out in the 1830s by Michael Faraday. This figure shows a coil of wire connected to a current measuring device such as a diarsenal galvanometer. Near the coil is a bar magnet. When the magnet is stationary, the galvanometer shows no current flow, as we would expect with no source of EMF in the circuit. But if we move the magnet either toward or away from the coil, the meter shows current in the circuit while the magnet is moving. If we hold the magnet stationary and instead move the coil and galvanometer, the same thing happens. So something about the changing magnetic field through the coil is causing a current in the circuit. We call this an induced current, and the corresponding EMF that has to be present to cause this current is called an induced EMF. The same effect occurs when the source of magnetic field is current in another circuit, as in this figure B here. We find that when the second coil is stationary, there is no current in the first coil, but when the second coil is moved forward or away from the first, so this has got a battery in it, so there's a current running through it, but when we physically move it about, then that's when we see changes in the galvanometer. If we just keep it still, we won't see any changes. So this is acting very much like the magnet over here. With these experiments, as well as those with the bar magnet, the essential feature seems to be the relative motion of the two parts of the setup. Finally, using these two coils here, you can see I've got one coil now connected in a circuit with a switch in it. So unlike this one, we've got a switch in this one now, and these are going to be held stationary with respect to one another, so there's no movement here, and all we're going to do is switch this on and off. So finally, using two coils set up in C here, we keep both coils stationary and vary the current in the second coil either by opening and closing the switch or by changing the resistance R. So we've got resistance, a variable resistance there, so we can keep the switch on and just keep varying that. That will give us different amounts of current in the coil. So we find that as we open or close the switch, there is a momentary current pulse in the first circuit. When we vary the current in the second coil, there is an induced current in the first circuit while current in the second circuit is changing. All these arrangements have one thing in common, which we'll explain in detail later on, that changing magnetic flux in the galvanometer circuit from whatever cause induces a current in that circuit. This statement forms the basis of Faraday's law of induction.